So in this lesson, I'm going to introduce the concept of rate laws, and we're going to be looking at rate laws quite a bit in this big idea. So a rate law simply shows how the rate depends on the concentration of the reactants. And so if you have a reaction, just a generic one that looks like this, then your rate is going to be equal to K, which is your rate constant, times the concentration of A, raised to its reaction order, which we'll talk about in one sec, times concentration of B times its reaction order. Notice M and N are different variables than little a and little b, and that's because when determining a rate law, you don't actually use the stoichiometry. So what is your rate constant? Well, your rate constant is your K, and the only way you can change K is by changing temperature. So otherwise, for a specific reaction, unless you change temperature, your K will always stay the same. So, as I said already, your M and your N are not determined by the simple stoichiometry of a reaction. Instead, the values of those exponents have to be determined experimentally, not stoichiometrically. So you can't just look at the equation and say, this is my rate law. Don't even try it. We'll get to a point where when we're manipulating reactions, you will be able to use it with reaction mechanisms, but for right now, you cannot use your stoichiometry. You need to determine it experimentally. So what exactly is your overall reaction order? Well, each reactant has a specific reaction order, which represents how the change in concentration is going to affect the rate. And we'll look at that mathematically in just one second. Now, the overall reaction order is simply the sum of each of the orders for each of the reactants. So let's say A is first order and B is second order, then the overall reaction order is going to be 3. Now, let's talk about the magnitude and the units for your rate constants. Magnitude-wise, the larger your K, the faster your reaction, which makes sense because rate equals K times your concentrations. And so the larger your K, the larger your rate, the faster your reaction. The smaller your K, the slower the reaction. And then finally, with respect to units, if I have a rate law that looks like this, my units for my rate are molar per second, and then my units for my concentration are molar. And so in order to determine what my units for my K are, I've got molar per second here equals my K times molar times molar. Well, in order to get rid of that molar squared and only have molar, one of the units for K needs to be molar to the -1. The other unit needs to be seconds to the -1 so I can have molar per second. So they're my units. So that problem solving is necessary because let's say, for example, you don't have molar times molar. Let's say you just have 1 molar, right? You don't have your concentration of B. Well, then the unit for your rate constant would just be seconds to the -1. So let's look at an example. Here I've got my rate law right there. The first question says, what is the reaction order of the reactant N2O5? It is first order because there's an implied exponent of 1. What are the units going to be? Well, since my rate is molar per second, my units for concentration is molar, then my K units are going to be seconds to the -1. Okay. For the next question, it tells me that I have this reaction. It gives me my rate constant. And the first thing it says is write the rate law for the reaction. Well, unless it tells me what the order is, I don't know it. You cannot just look at your reaction, but notice it does say that the rate law is first order. So I'm going to write my rate law. It's going to be rate equals my K times the concentration of N2O5 because N2O5 is first order. Now, if it wants me to find the rate of the reaction and gives me the concentration of N2O5, I know my K, it's 4.82 times 10 to the -3 that's given to me. So I can plug that in to solve for my rate. And so my rate here is going to be 1.16 times 10 to the -4 molar per second. So there are 2 different ways of determining the rate law experimentally. The first one is actually pretty nice and easy. Here's what you do. It's called determining the rate law by inspection. So what you're going to do is you're going to look at the changes in concentration and rate and figure out what the order is. So let's look at this example. What you're going to do is say, all right, how does the change in concentration of A impact the rate? If A doubles, does my rate double? If so, then you have first order. If my concentration of A doubles, but my rate quadruples, that tells me I have second order. If my rate of A doubles, but my rate increases by a factor of 8, that means that I have a third order. So let's look at this. What I'm going to do is I want A to change, but I don't want B to change for this first determining, because if B also changes, that doesn't tell me how A impacts the rate. So if you look at experiment 1 and 2, A doubles while B stays the same. So as A doubles, if you look at your rate, the rate also doubles, which tells me that A is a first order, because as it doubles, the rate doubles. Now I want to look at B. So if I look at experiment 1 and 3, the concentration of A doesn't change, but the concentration of B doubles. Well, as B doubles, so does the rate, which means that it's for first order as well. And so the rate is going to simply be K times the concentration of A times the concentration of B, because they're both first order. Now it asks me to determine the rate constant. This is really nice and easy. You can take any information from any of the 3 experiments, plug them in, and then solve for K. And so what I did was I used the first experiment. So my rate is 4 times 10 to the negative 5th. That equals my rate constant, since I don't know that, times the concentration of A times the concentration of B. And now I'm going to solve for K. Now notice I included my proper units, molar to the negative 1, seconds to the negative 1, because the overall order of this reaction is 2. The second way of determining your rate law is if it's not so obvious or they're not two comparable trials, you're going to have to do this mathematically. So let's look at this. In this example, I look and I see, all right, I see 2 experiments in which the initial concentration of B stays the same. Awesome. I can determine the rate of A. So from experiment 1 to experiment 2, the concentration of A triples. From experiment 1 to experiment 2, the rate of the formation of C triples as well. So I know that A is first order. Now if I try and do the same thing for the concentration of B, notice none of the concentrations of A stay the same. And this is where it gets just a tiny bit tricky. What I'm going to do is I'm going to take 2 experiments. So I'm going to look at 2 and 3. The concentration of A doubles. It goes from 0.75 to 1.5. Notice that the rate quadruples. Okay? So what that tells me is that since B also doubles, then B must be first order as well, because as A doubles, B doubles, and the rate quadruples. If instead it had been that the rate increases by a factor of 8, but everything else stays the same, then the initial concentration of A doubles, but since B still doubles, it would have been second order, because it would have been 2 times 2 to the second, which equals 8. So that's what I'm meaning. It's not obvious. You're actually having to use math. So A is first order, B is first order. For this one, you'll get more practice, I promise. And so the rate law is just going to be rate equals K times A times B. Now, let's look here for the next 2 questions. It says, determine the initial rate of change of concentration of A in experiment 3. So the first question is, whoa, what's going on? Don't I have all of the rates? Well, if you look, that's the initial rate of formation of C. And so that tells me I can use the relationship between the rate of C and the rate of A. Now, the rate of disappearance of A, what it's going to be is negative 1/2 times the rate of change of A is going to be equal to the rate of change of C. Okay? Based on the stoichiometry that we looked at in the previous lesson. Now, since I know the rate of C for experiment 3, 5.3 times 10 to the negative 3rd, I can plug that in, and then all I have to do is multiply both sides by negative 2. And so the rate of disappearance of A is going to be negative 1.1 times 10 to the negative 2nd. And that's my final answer. Now for D, it says determine the initial value of B in experiment 4. Well, here's my thing. I have my rate law. So I'm going to use an experiment, either 1, 2, or 3, in order to determine my K first. Because I need to solve for B, I can't have 2 variables in an equation. So I used the first experiment. So my rate was 4.3 times 10 to the negative 4th. That's going to be equal to K times the concentration of A times the concentration of B. So my K was 2.3 times 10 to the negative third molar to the negative 1 second to the negative 1. Now I can plug that into my rate law again, but use the data from experiment 4. And so my rate here is 8.0 times 10 to the negative third, which equals my K, which is 2.3 times 10 to the negative third, times my concentration of A, which was 1.75, times my concentration of B. So my concentration of B, rounding, is going to be 2.0 molar.